Now, when you read up in section 3.7 about the leveling effect, the textbook uses, right there, I don't want to say difficult words, they just use the chemistry terms. And if you're not familiar with them, sometimes reading sentences with chemical terms maybe sounds a little confusing. So what I'm going to do is just put it in my own words and just keep it as simple as I possibly can. And then you need to be able to read the text from the book and relate it to what I'm telling you, what the leveling effect is. So simply put, is if you have a reaction that you want to do, let's say take this alkyne and treat it with a very, very strong base. Okay. This is called, when it's negatively charged like this, that's called an amide. And what we want to do is get that to react and take off that proton to form this, what's called an alkylide ion. That's the reaction that we want to do. But reactions, most reactions they need to occur in a solvent. You can't just take these two reagents here on the screen and just throw them at each other and make them react. They need to be in a solution. So you need to choose a solvent. So the leveling effect is asking, which solvent do you use? So let's think of an ideal situation. When you pick a solvent, you want a solvent that does not react with either of your starting materials or your reactants. You want this reaction to take place. That's what you want to have happen. So the solvent, whatever it is, cannot interfere with that. If the solvent interferes with that reaction, then you're not going to get that reaction to occur. And then you'll be like talking to your PI, I spent 20 hours trying to make this thing and nothing's happening. Well, is your solvent reacting? You have to ask these questions. So, what solvent, then the next question is like, what solvent do you use? Well, let's just pick a common one. There's water. What if we put those two reagents into water? Would that be a good solvent? And the way that you answer that question is you typically take the charged species or the base and you ask, does it react with water? There we go. So you look at the equilibrium there, I have to have a negative charge. Now you ask yourself, does this reaction occur? Grab the proton. That's not a good arrow. Grab the proton like that. So what's our product going to be? NH3 plus hydroxide. Now, do we want water to react with our solvent? Or do we want water to react with our reagents? No, we don't. So how do we know if it's reacting or not? Well, this is a simple acid-base question. Which side is favored at equilibrium? If it's the right side, if the right side's favored, then that means it's reacting with the solvent. If the left side of the equation is favored, then it means it's not going to react with the solvent at all. All right? Equilibrium, favored to the left, means that the nitrogen species in the water is not reacting. If it's favored to the left, right? Is that what that equation is telling us? So how do we figure out which side of the equation's going to be favored? What's your first step when I ask you that question? Which side is favored? What do you do? Where's your acid? Where's your base? You see, I don't need to tell you, find the acids, find the conjugate bases. You just need to know how to just do it. If I ask a question, which side is favored at equilibrium, you know, we have to first identify our acid. On the left side, which is our acid class? The nitrogen species or water? Water. So we said that's our acid, so that has to be by default the base. So that would make that the conjugate base, conjugate acid. What's the next step in order to determine equilibrium? pKa's? So what's the pKa of water? We'll say 16, make math easy. And ammonia? It's a nitrogen species. It's an amine. 38. Okay, based off of that data, which side is favored? Products or reactants? Okay, where's the weaker acid? On the right side. So equilibrium is favored to the right, because equilibrium favors to the weaker acid. Does that make sense? I don't think it is. How far to the right is it favored? 38 minus 16, what's that? Is that 22? Is it 22 times favored to the right? No. It's 10 to the 22. Okay. So when that... Would it be negative? No, it's just always absolute. Just absolute values. Just going to be a positive value there. So it's 22 times favored to the, or 10 raised to the 22. And so, is this a good solvent choice? No, because it's reacting. When your value here is greater than, when the difference here is greater than 3, okay, greater or equal to 3, that difference between the two pKa's, this reaction is pretty much irreversible. It's just all to the products in an irreversible fashion. However, if the difference of these two numbers right there is less than 3, then the reaction is reversible. All right? So what do reversible arrows look like? Looks like that. What would an irreversible arrow look like? Just one arrow. It's like it's all going that way. So what you want to find, ideally, is you want to find a solvent that says go to the left irreversibly. And so a good solvent that you might choose is the problem that I asked you guys to solve for today. All right, remember when I said look at a hexane molecule and treat it with the base? Where does equilibrium go? So hexane would probably be a good one to do that reaction. So that's what the leveling effect is. Does your solvent react with your reagents? And the way that you figure that out is doing acid-base chemistry. Questions? Thoughts? The next thing that you need to freshen up on is section 310. So 310 in the textbook is Lewis acids and Lewis bases. This is something that you've already been taught. And so this is just a review, so I'm not going to go into it other than just telling you guys, hey, you need to remember this. But the way most students study is that they study based off of the lower Bloom's taxonomy, meaning just regurgitate information, regurgitate definitions, and that's where most students stay. And it's really, I think, no fault of your own because that's how you've been trained in middle school and high school. Just here's some facts, just spit it out. Very rarely do you actually think about it and apply it. And so this is kind of back to the analogy. Lower Bloom's is how do you ride a bicycle? You read a book about it and you watch a YouTube video, but you never get on the bike. Upper Bloom's is where you actually get on the bike and you experience it. So on my exams, will we ever give you a definition problem? Probably not, because that's lower Bloom's. So you need to be able to look at a reaction, look at reagents, and say, hey, which one's the Lewis base, which one's the Lewis acid? Yes, you need to learn the definition, but you need to take it up a notch by being able to apply what that definition means. All right? So make sure you review your Lewis acids and their definitions and applying what that definition actually means. So now, with that, we can get back to the cardinal rule and applying those principles that I taught you in the video. So let's do a relatively simple example here. I'll give you 4 molecules here, and I want you to rank them. Okay, so you have those 4 molecules. What I want you guys to do is take a few minutes and rank them from the most acidic to the least acidic. And then we'll see what you guys come up with, and we'll go through it. And then we'll give you more of a test caliber type of question.